In this video, we will solve maximization problems graphically. So here you see we have our objective function, which is called p of xy, and then it's subject to these four constraints. Step one is to graph the feasible region. So in order to graph the feasible region, we will need to take these four constraints and graph them. So graphing them includes graphing a line and shading the region either to the left or right or above or below. So this first constraint I will graph will be y is greater than or equal to negative x plus 2. So you see all I did there was isolate y so that I could graph it in the form y equals mx plus b. So let's go ahead and do that. So this is a y-intercept of positive 2 and a slope of negative 1. So we'll just go down 1, right 1, and we can extend it to the left the other way, and we'll continue drawing that line. You'll notice I drew a solid line because it is greater than or equal to. Now for the greater than part of the line, that's going to be the region above the line or otherwise to the right of the line. So to denote that, instead of shading, because this might get a little bit messy, I'm just going to draw these little arrows that tell me I'm looking to this side of the line. Okay, my next constraint will be that y is less than or equal to negative 2x plus 8. Again, I just isolated y. So this is a line with a y-intercept of 8 and a slope of negative 2. Down 2, right 1. Down 2, right 1. So continue sketching that line and then try to see if you know where to shade it. So there's the line, and we want to shade the region less than or equal to. So we could plug in a point on one of the sides, or we may just know that the less than piece is always to the left or below the line. So that's going to be to this side, remembering that you can always use Desmos to check your answers. So you can see we're starting to form that feasible region. It's going to fall in between these two lines right here. So let's see if these two constraints can help us figure out or help us kind of zone in. So next we have 2y is less than or equal to negative x plus 8, and we still want to isolate that more. So we're going to divide by 2, and we get y is less than or equal to negative 1/2 x plus 4. So now we need to graph the line, the y-intercept of 4, 2, 3, 4, and a slope of negative 1/2. Down 1, right 2, down 1, right 2, and we can continue that to the left. So finish drawing this line, and then we want it to be less than or equal to. So there's our line, and less than or equal to tells us to shade below the line. So you're starting to see what that feasible region is. So less than or below would be this region down here. And now that we can kind of see it, maybe we want to fill that in and shade it. There it is. And we still have one more constraint, actually two. We want both x and both y to be greater than 0. So remember, those are our axes. So we can draw right here. This would be that y is greater than 0. So there's our line. Y equals 0, and we want it to be above that line. So anything up this way, up there. So that cut off a piece of that feasible region. And then we will also want the x values to be greater than 0. So we'll draw a line here. And we want them to be positive, which means we want them greater than 0. So finally, let's zoom in a little bit so we can take a look at this. We have our feasible region marked by some corners. So here's a corner here, a corner here, a corner here, not as exact, and a corner here. Oh, I missed one. And that is not one. Oh, undo. You get it. Okay, so I did, sorry about that. This would be one of our corners. 1, 2, 3, 4, 5 corners. And now let's go ahead and label those corners. So we have 2, 0. We have 0, 2. We have 0, 4. We have 4, 0. And then this is this oddball right here. So you see that it doesn't cross exactly at a nice number. So it's where that blue and the pink one are crossing. So we want to know where those two lines intersect. So we want to know, where do these two meet up? Where do they cross? Where do they intersect? Where is their solution? Do you remember solving systems of equations? We want to know, what is the solution to this system of equations. We can figure that out. We just have to set them equal to each other and solve for x and for y, and then we'll know what that point is. Now, another way you could do it is to just graph this in Desmos, and you'll find out what that point is. I'll let you determine how you want to do it. Again, I'll just set this up for you. So to find this point, we would just set, where is negative 2x plus 8 equal to negative 1/2 x plus 4. And then we would solve for x and we would solve for y. And we would see that this point is at 8/3, 8/3. You can always check your answer in Desmos. So step 1 was to graph the feasible region. Step 2 is to identify the critical points, which we did. So we'll just list them here again. So we found 0, 2, we found 0, 4, 2, 0, 4, 0, and 8/3, 8/3. Now we can use these critical points. No, you can't talk. Now remember, this was a maximization problem. So we have identified where our maximum might occur, and now we need to plug it into our objective function. Remember, that was called p of xy. I'll write down what it is, 15x plus 6y. And now we need to take those critical points that we determined from our feasible region, and we need to plug them into our objective function and see which one gives us the largest value, the maximum. So we can take each one of these, will be an x and a y. We'll plug them into p, and we'll see which one gives us the largest value. So I'll do one with you, and then I'll leave the rest to you. So let's plug in the first one, 0, 2. 15 times 0 plus 6 times 2. Well, that just gives us 12. So keep doing these. I'm going to pause the video, and you can play it when you're ready to check and determine which one's the largest value. So here you see that we ended up with these values that came out of our objective function, and we simply want the largest one, which is 60. So the objective function has a maximum value of 60. This occurs at 4, 0.